Hello everyone. In this video, we're going to discuss the solution of the gas dynamics and propulsion questions of GATE Aerospace Engineering 2021 paper. So in this year from GD and propulsion, around 20 marks, questions of around 20 marks came, consisting both 1 marks and 2 marks questions. So we'll see the solution of them in this video. Okay, so the first question, this is a 1 mark question, and this came from gas dynamics part. So here two different flow pattern in a convergent divergent nozzle have been given, and we are asked to find out which pattern corresponds to an over expansion and which pattern corresponds to an under expansion. So to see this solution, to understand the solution, we have to understand different flow pattern possible inside this convergent divergent nozzle. Okay, so let's consider this convergent divergent nozzle, the chamber pressure and chamber temperature of which are P0 and T0 respectively, and PB is the back pressure. So back pressure is the pressure at which the nozzle discharges the flow. Okay, and this back pressure can be regulated by means of a pressure valve. So if we see the different flow patterns, so let's if we see the like pressure variation of pressure with time. So initially let's consider a condition when the back pressure is equal to the chamber pressure. So in such condition, as there is no pressure gradient, so no flow will take place, and that condition corresponds to this plot. Okay, so here this is the first condition where back pressure is equal to chamber pressure and there is no flow taking place inside the Condi nozzle. Now, if we reduce the back pressure slightly, as there is pressure gradient now with respect to this chamber pressure, so flow will start taking place inside this Condi nozzle. Now, but still, if the back pressure reduction is very minute, the flow will still be subsonic inside the nozzle. So in the convergent, in such cases, in the convergent part of this nozzle, the flow will accelerate and the Mach number reaches maximum at the throat, and then again decelerate in the divergent portion. Now, if we keep on reducing the back pressure, we'll reach a certain condition, a certain value of back pressure, for which the Mach number of the flow at the throat goes barely sonic. So let's consider that back pressure as PB1. Okay, so this condition PB1 at which the Mach number at the throat, the flow Mach number at the throat goes barely sonic. So this is the throat where the Mach number is 1, but the flow still decelerates inside the divergent portion. So the flow in the divergent portion is still subsonic, and this condition, so this is the flow for this condition, and this condition is entirely subsonic isentropic solution of the flow. Okay, now for each convergent divergent nozzle, there is one particular back pressure for a specified chamber pressure, for which the flow inside the Condi nozzle continuously expands, and that back pressure is defined by the designer, and which is known as this design back pressure. So in this design back pressure, flow continuously expands inside this convergent divergent nozzle, and that condition is actually known as supersonic isentropic solution. So this is supersonic isentropic solution. So what happened when we reduce the back pressure from PB1? So if you reduce the back pressure from PB1, the Mach number, as it has already reached sonic inside the at the throat. So the convergent part of the duct remains unaffected. So even if we reduce the pressure from PB1 between this range PB1 to PBD, we will see no change in the flow in the convergent part. So it will follow this path only, and then but the divergent part, there will be some physics going on inside the divergent part. Okay, now, so two conditions we have seen. One is when the flow is completely subsonic and the solution is isentropic, that is this condition, and one is flow is completely supersonic and flow continuously expands inside the nozzle, and that condition is this one, which is supersonic isentropic solution. Now let's consider two different cases. One is when the back pressure, when you reduce the back pressure further below this design back pressure. Okay, so let's consider that condition. So let's see, this is the PB, uh, which is less than the design pressure. So what will happen in the convergent divergent nozzle in such condition? So again, the convert the this convergent part, flow at the convergent part remains unaffected, and it follows this path. But just at the exit plane, just before exit plane, the flow sees a certain pressure change, right? So because here at the exit plane it will see a pressure which is less than the design pressure, so the flow has to match this pressure change. And as we know that across an expansion wave, the pressure, static pressure, always decreases, and across an oblique shock the static pressure increases. So the only means by which the flow can adjust itself to this reduced back pressure at the exit is by forming an expansion wave at the nozzle exit, right? So here the pressure will undergo this, like this. The flow pattern will be like this, and this will be achieved by this expansion wave at the exit. So in this condition, the as we are saying that at the exhaust plane, the flow is still under expanded. So it has to go further expansion to match with the back pressure. So that's why this condition is known as under expansion. So this condition is under expansion. So that means when expansion wave is formed at the exit of the nozzle, the condition is known as under expansion. Okay. So now let's consider. So now let's consider another condition. When the back pressure is greater than this PBD, when the back pressure PB is greater than this PBD but less than PB1. So let's consider it somewhere here. Okay, so in such condition, what will happen in the flow? So again, at the convergent part of the duct, no change will take place, so it will remain unaffected. And in the divergent part, it will become like this, but just near the exit plane. So if this back pressure is just slightly more than this PBD, the design pressure, so in the near exit plane, the flow will experience a certain pressure jump, right? And so the flow has to match with this higher back pressure, and the only way the flow can do that is by forming an expansion wave. So it has to match with this increased with this higher back pressure. So the only way by which the flow can do this is by forming an oblique shock. So the flow pattern will be like this, and this condition is known as overexpansion. So this condition is known as overexpansion. So what we have seen then, that when there is this oblique shock formed at the nozzle exit, the condition is known as overexpansion, and when the expansion wave is formed at the exit of the nozzle, the condition is under expansion. So this is expansion wave. This is oblique shock. Okay. So now let's see the options. So here in the first pattern, the oblique shock is formed at the nozzle exit. That means this flow pattern corresponds to over expansion, and the second pattern, expansion wave, is formed. Hence, this pattern corresponds to under expansion. Hence, option A is the correct option. Okay. So now let's move to the second question. So this is again 1 mark question. 1 marks question, and it is asked that the combustion process in a turbo shaft engine during ideal operation is, and then 4 options are there. So in a gas turbine uh, engine, the combustion process in ideal case always takes place at constant pressure. Okay, so if we see the PV diagram inside a gas of this gas turbine engine, it will be like this. Okay, so this is 1, 6. So 1, 2 corresponds to this inlet of the engine. 2, 3 corresponds to compressor. This is combustion chamber. This corresponds to turbine. This is nozzle, and this is heat rejection into the atmosphere. Here, okay. So as we can see that the process inside in the combustion chamber in ideal cases is always a constant pressure process, and this constant pressure process is in combustion chamber flow takes place at constant pressure, and this constant pressure process is known as isobaric process. Okay, so hence this is the correct option. And let's see the other options also. So option A is isentropic, which means it is reversible adiabatic. Reversible adiabatic. So in the combustion chamber, heat addition is taking place, so it's definitely not adiabatic. So this option cannot be correct. And isobaric is constant pressure process. Okay. Isochoric is constant volume, and isothermal is when the temperature is constant. And again, in combustion chamber, heat addition is taking place and temperature is increasing, so this cannot be correct option. Okay, hence B is the correct option, isobaric process. Next question. How does this specific thrust of a turbojet engine change for a given flight speed with increasing in flight altitude? Okay, so the thrust of a turbojet engine is denoted as T equal to T equal to m dot minus vi. Okay, where m dot is this mass flow rate in the inside the engine, mass flow rate in the engine. Ve is exhaust velocity, and vi is basically flight velocity. Okay, this is the and of course we are ignoring the pressure thrust in this equation. So, and the specific thrust is thrust per unit mass flow rate, hence it will become ve minus vi. Specific thrust is just a difference in the exhaust velocity and the flight velocity. Okay, So, and this VE, the exhaust velocity, this is nozzle exhaust velocity. So if this can be calculated as by doing this energy balance across this nozzle. So you see this nozzle, see this is inlet. So this is total temperature at the inlet, and this is exit temperature, and let's see the exhaust velocity is VE. So if we do energy balance, it will give us that COI equal to CPTE plus half rho VE square, and hence VE we will get as under root of 2CP TOI minus TE. And this TE is the exhaust temperature, and if we consider that this nozzle is exhausting the fluid is being discharged from the nozzle at atmospheric condition, so this TE can be written as TE TA, atmospheric temperature, right? Now as we increase altitude, the temperature decreases, right? So the so equation of specific thrust which we got, specific thrust is VE minus VI, and if we, so as the flight velocity is constant, so I is constant, and VE depends on this TE, which is the ambient temperature. And as the altitude increases, ambient temperature decreases, right? So TE decreases, and that means, so as altitude increases, TE decreases, right? And as TE decreases, the exhaust velocity increases. So, and if exhaust velocity increase, then specific thrust, from this equation we can say that specific thrust will also increase, and specific thrust will increase, right? So with increasing altitude, specific thrust will increase. So this is the correct option, increase harmonically. Okay. So third questions: how does the propulsion efficiency of a turbofan engine How does the propulsion efficiency of a turbofan engine operating at a given Mach number and given altitude change with increasing compressor pressure ratio? Okay. So the propulsion efficiency, the variation of propulsion efficiency for a turbofan engine with compressor pressure ratio is like this. So pi c is the compressor pressure ratio, and eta p is the propulsion efficiency. So the variation would be like this. Okay. Uh, so the explanation of this is, we know that eta p is 1 plus 2 by VE by VI, but again VE is the exhaust velocity, nozzle exhaust velocity, and VI is flight velocity. And if we see the variation of exhaust velocity with back pressure, with this uh, compressor pressure ratio, the variation will get like this. So initially, with increasing compressor pressure ratio, the exhaust velocity increases, right? Exhaust velocity increases, and this happens because as we increase the compressor pressure ratio, the compressor exit temperature will be higher, which means the combustion entry temperature is also higher. So with same addition, the same amount of fuel addition inside the combustion chamber, the combustion outlet temperature or turbine entry temperature will be higher, which means the exhaust velocity will be higher. So that's why initially with increasing compressor pressure ratio, the exhaust velocity increases. But this does not go on happening as we keep on increasing the compressor pressure ratio, because as we know that compressor operates at an adverse pressure gradient. So if we keep on increasing the compressor pressure ratio beyond a limit, then on the compressor blade flow separation takes place, and that's a catastrophic condition. The engine performance deteriorates. So again, when we increase beyond that limit, the engine performance deteriorates, and the thrust reduces, and exhaust velocity reduces. Okay, so this is this part, that part. Now, and at this part, as at this part, when the exhaust velocity increasing with this increasing compressor pressure ratio, from this equation we can see that as VE will increase, eta P will decrease, which means propulsion efficiency will decrease up to this limit. Now again, when if we further increase compressor pressure ratio, the exhaust velocity starts reducing. So from this equation, if VE reduces, eta P will increase. So from at this part, this part corresponds to that flow. So here is this is the total variation of propulsion efficiency with compressor pressure ratio. So it first decreases and then increases. So this is the correct option. So third, question number 8. This is also a 1 mark question. Okay, so in the solid propellant rocket so thrust produced by solid propellant rocket is given as 25 meganewton, which means equal to 25 meganewton, and it is fired for 150 seconds. The specific impulse is given as 2980 Newton second per kg, and how much propellant is burned during the rocket operation. Okay, so this specific impulse ISP by m dot is given as 2980, right, and T is given as 25 meganewton. So from this equation we can get that m dot is m dot will be 8, so 25 into 10 to the power 6 divided by 2980, so we'll get it as 8389.26 kg per second, and this m dot is the propellant burned per second. Okay, so the total propellant burned, the mass of the total propellant burned is m equal to m dot into T, as it is burned for the duration of 150 seconds. So if we do this multiplication, we will get it at 1.258 into 10 to the power 6 kg. Hence this is the correct option. Okay. So next question, it is also an one next question, and so the shape of the supersonic diffuser that slows down supersonic flow to subsonic flow is. Okay, so different options are there: converging, diverging, converging, diverging, and diverging, converging. Okay, so in a converging nozzle, in a converging duct, for a supersonic flow, the velocity decreases. Right? We know that the area velocity relation, which is this dA by A square minus 1 du by u. So as in the converging duct, dA is negative, so and m square minus 1 is always positive for supersonic flow, right? Whereas dA is negative, so du will be negative, hence it will decelerate the flow. So in this, the u will decrease, and so it will decelerate the flow, but the the flow at the discharge will still be supersonic. So if we see, this is m2 and this is m1, so m2 is always less than m1, but it is still supersonic, so m2 is greater than 1. Okay. So this is not the correct option. Now let's see a divergent duct. Okay. So a divergent duct, if the for the supersonic flow, you can see that dA is positive, and as m square minus 1 is also positive, hence du has to be positive, so it will accelerate the flow. So u will increase inside the duct, and here flow, the Mach number will be higher than the flow Mach number at the entry. So m2 will be greater than m1 in this case. So again, this is also not the correct option. And then converging, and if we see this converging diverging duct, if we see a converging diverging duct, a flow of a supersonic flow. So in the convergent part, the flow will decelerate, and at the throat, it will the flow Mach number will become sonic, and in the divergent part, it will further decelerate, and at the exit, it will be subsonic. Okay, so here m is less than 1. So in the convergent divergent duct, we get a subsonic velocity at the exit of the nozzle for a supersonic velocities for the supersonic flow inside the nozzle, right? So this is the correct option. And diverging converging duct is also not the correct option, because uh, as you can guess that so this is the divergent convergent part duct, and if this is supersonic velocity, so in the divergent part again the velocity will further increase, right? And the velocity will further increase, and we would not get a subsonic velocity at the exit, so m will always be greater than 1 here. So this is the correct option, converging divergent duct. So the next question, that is oblique shock has been given, and it is multiple choice, MSQ, multiple select questions. So let's say MSQ, and it is also of marks 1. So the question has been basically asked on the flow properties of across oblique shock. So the options are the total pressure decreases. So yes, because across an oblique shock, the entropy always increases, and hence total pressure decreases. So this is the correct option. Second option, Mach number based on velocity tangential to the shock decreases. So as we know that the tangential component of the velocity across the oblique shock remains constant, right? So if the upstream of the shock is noted as 1, and downstream is 2. So U, okay, so U T1 will be equal to UT2. Now across an oblique shock, temperature, static temperature always increases. So T2 will be greater than T1, and hence A2 will be root over of gamma R T2, which is again greater than A1, as T2 is greater than T1, right? So the Mach number M2, which is equal to the tangential component of the, I mean the Mach number, which is on the, which is based on the velocity tangential to the shock. So this is based on tangential velocity. Tangential velocity will be A2 is less than M1, right? Right, because the velocity is same, ut2 equal to ut1, but a2 is higher than a1, so m1 will be less than m2. So this is also correct option. The total temperature remains constant, yes, because across an oblique shock, the enthalpy remains constant, and hence total temperature also remains constant. And in this option, Mach number based on velocity tangential to the shock remains the same. Based on velocity normal to the shock decreases. So this is not the correct option, because as we have seen that the Mach number based on velocity tangential to the shock actually decreases. This is not the option. So the correct options are A, B, and C. Okay, so this is a question on moving shock, and this is a single MCQ type question, multiple choice question, and this is a marks 2. So here basically a shock moving into a stationary gas can be transformed to a stationary shock by changing the reference frame, and as shown in the figure, which of the following is true relating to the flow properties of the two reference frame, right? Okay, so here what they're doing, so first they have given this moving shock, okay, and which is a normal shock which is moving at a velocity vs, and they are transforming this problem to a stationary normal shock problem by changing the reference. So this can be think of this way. So this is a shock, and in, let's see, this is in this coordinate frame, okay, xy. And if we consider an observer here, observer standing on the stationary coordinate system, it will see that the shock is moving at a velocity vs inside the flow, and the flow is static, right? So here the flow is static and shock is moving. Now if we just the same physical condition can be think of in a different way. So if we just transform this coordinate system to a moving coordinate system, which means the, if we think of a coordinate system which is actually sitting on this shock, so then so you can think of this in this way. If we think that this observer, which was earlier standing on the stationary coordinate system, is now sitting on this shock itself, right? So the relative velocity between the observer and the shock becomes zero. So what will the observer see in this condition? The observer will see a static shock, right? As the relative velocity between the observer and the shock has become zero. So it will see that the shock is static, but the flow is moving, right? So in this way you can transform this moving normal shock problem to a stationary normal shock problem. All right. So these are this P1, T1, GO1, all these are the downstream condition in this moving shock, in case of moving shock, and P1 dash, T1 dash, all are downstream condition in case of stationary shock. Now all these stationary, so P1 and T1 and ρ1, these are the static properties, pressure, temperature, and density. And all these static properties are computed by an instrument which is moving with the absolute flow velocity, right? So the relative velocity between the instrument and the flow has to be zero. So this static properties are measured such a way that this is independent of the velocity of this observer. Okay, so and hence, so by on this coordinate transformation, the static properties doesn't change. So this is one very important point in this moving shock problem, that changing the coordinate system doesn't coordinate system from stationary to moving stationary to moving does not affect the static properties. Okay. And hence this P1 will be equal to T1 dash, T1 will be equal to T1 dash, and ρ1 will be equal to ρ1 dash. So from this condition itself, we can see that the correct answer is between B and D, and we can easily discard A and C, right? Now let's explore it further. So as in this moving or normal shock condition, the shock is moving and the fluid is static. So in this case, the fluid velocity is actually zero. But in case of stationary shock problem, the shock is static, but the fluid is moving at a velocity Vs, right? Hence, this is U is greater than zero. U dash. So let's U1 and this is U1 dash. Right now here we have seen that P1 is equal to P1 dash, T1 equal to T1 dash, but U1 equal to 0 and U1 dash greater than 0. Since from this condition we can easily figure out that total temperature T1 dash will be greater than T1, right? Because T1 and T1 dash both are equal, but U1 dash is greater than 0 and U1 is 0. Hence, T1 dash has to be greater than TO1. And also, PO1 dash is greater than PO1. Right? Hence, PO1 dash is greater than PO1 and TO1 dash is greater than T1. So, these options satisfy all these conditions. And D is the correct option. And okay, so this is a 2 marks question. Okay, so the flight velocity has been given, which is Pi has been given to 70 meter per second. The enthalpy of the incoming air is given, Hi, which is 260 kilojoule per kg. Uh, enthalpy of the exhaust gas nozzle at the nozzle exit is given, is 9 joule per kg. And the ratio of mass flow rate to the fuel mass flow rate of the fuel and air is equal to 0.019, and the chemical energy of the fuel is given as 44.5 megajoule per kg, and the combustion process is considered as ideal process, and the total heat loss from the heat equation from the engine is 25 kilojoule per kg. Okay, so we're supposed to find out the exhaust velocity, exhaust jet velocity, right? Now in this problem there is no information has been given for compressor and turbine, so we can consider them as ideal case, ideal compressor and ideal turbine with efficiencies equal to 1. Okay, so here we can do this energy balance equation across combustion chamber. So at the total enthalpy, total energy at the engine inlet will be equal to this 260 kilojoule, 260 joule plus half into, so this is, let's consider this, the mass flow rate of air inside the aircraft is ma dot. Okay, and this is so half ma dot into 270 square, so this is the total energy at the entry of the aircraft. And as we are considering the compressor to be ideal and with efficiency 1, so this will be the energy, there will be no loss taking place inside the compressor, and this will be the energy which is available at the entry of the combustion chamber, right? So this is the, so if we do the energy balance equation across the combustion chamber, what we will get? So this is the total energy which is at the entry of the combustion chamber, and then inside the combustion chamber the fuel is being added, right? So the energy which is coming from fuel is, sorry, the energy which is coming from fuel is F into this 44.5 into 10 to the power 6, right? And this is the amount of energy which is available at the combustion exit. H4. So if we just, sorry, here I have done a mistake, so this will not be F, this will be mf dot, right? Now we can take ma dot common from both sides and make it as a ratio of ma dot by m dot ma dot, and if we substitute all the values we will get HO4 as, HO4 will be equal to 10657 per kg. Okay, now here it has been given that the total loss of heat from the engine to the ambient is 25 kilojoule per kg of air. So we'll have to incorporate that in the solution. So the total available energy is this 1120657.5 minus 25 into 10 to the power 3 joule per kg, right? So this is the amount of energy which is, this is the amount of energy which is available at the nozzle exit. So if we again do the energy balance equation across the nozzle, so this HO4 dash, that will be equal to the enthalpy at the exit of the nozzle, which is given as 920 kilojoule plus the kinetic energy of the exhaust gas. Right. So if we substitute this value, this, then you will get as 606.05 per second. Okay. So this is the answer. Okay. So the next question. This is a question from rocket propulsion, and the specific impulse of the rocket you have to find out. And the provided informations are the generated. Okay. So T naught is given as Kelvin, which is the chamber pressure, and P naught, the chamber temperature is to 2100 Kelvin, chamber pressure is 14 megapascal, and hot gases are expanded ideally. Ambient temperature, ambient pressure is given as 0.1 megapascal. It is going through a convergent divergent nozzle, having the throat area is 0.1 meter squared. So the universal gas constant is given as 8314 joule. So the specific gas constant will be R naught by M, which is should come something around 377.9 joule per kg Kelvin, and this M is given as 22, right? So if we substitute this here, we'll get this, and gamma is given as 1.32, which is 9.81 meter per second square. And so the Cp gas Cp will become, you can calculate as gamma r by gamma minus 1. You can substitute this value here and we will get Cp as something around 1.83 joule per kg Kelvin. Okay, so we have to find out what is the specific impulse of this rocket. So specific impulse can be calculated as T dot T by thrust by the exhaust mass flow rate multiplication with gravitational constant. So this M, this thrust is again can be written as M dot into exhaust velocity. Hence, this can be simplified as E by G. Okay. Okay. Now the exhaust velocity from the nozzle that we have to calculate. So exhaust velocity from the nozzle can be written as, so exhaust velocity from the nozzle can be calculated as from this energy balance equation across nozzle. Okay, so if we okay, so in this nozzle, if this is the nozzle entry, this is exit, so this is TOI. So we doing energy balance across the nozzle, we will get as CPTE plus half rho half half Q square. Okay, so from here we will get U as 2CP TOI minus TE. And as the nozzle is discharging the flow at the atmosphere, so TE will be equal to T ambient temperature, and TOI is so this basically the chamber pressure. So TOI will be equal to TO. Okay, so you can just take TO common and you will get as TA by TO, and this TA by TO can be written as PA by PO to the power gamma minus 1 by gamma, right? So this comes from isentropic relation. So if we substitute it here, what will we get? We will get UE as 2cp t naught 1 minus pa by p naught to the power gamma minus 1 by gamma this, right? So substituting all value we'll get ue as 2138.02 meter per second. Now if we substitute that ue and g here in this equation of specific thrust, we'll get I is equal to 2138.02 divided by 9.38, right? So it will come around 16.23 seconds. So this is the correct option, correct answer. Next question. So here at a axial compressor stage, the velocity triangle has been given, and we are asked to find out the blade velocity. Okay, so here C2 and C1 are the absolute velocity component. So C2, C1 are absolute velocity component, and W components, W1 and W2, these are relative velocity component, relative velocity, and this angle is relative angle, relative exit angle basically, because two condition is, the exit condition is denoted as 2, okay, exit of the stage. So this is relative angle, and this angle is absolute angle. So let's just consider this angle as alpha 2. Okay, so and we are asked to find out u. So u is basically peripheral velocity. Okay, so u we have to find out. So from this velocity triangle, from this triangle, we can see that u is so can this is C2 sine alpha 2. From this triangle it can be, okay, so from this triangle it can be written as this length will be C2 sine alpha 2, and from this triangle this length will be W2 sine 30 degree, right? Hence u will be equal to, W2 sine 30 degree plus C2 sine alpha 2. Now this is the axial velocity, and the axial velocity CA2, which is equal to, again from this uh, trigonometry you can find out that this is equal to C2 cos alpha 2 equal to, from this triangle, W2 cos 30 degree, and C2 is given as 240 meter per second, and C1 is given as 140 meter per second. So if we substitute this here, we will get alpha 2 as 60 degree. Okay, so from this equation now from equation 1, we can substitute this value of W2, C2 and alpha 2, and you will get it as 277.84 meters per second. Okay, this is the correct answer. Okay, so next question. This is question. So in a combustion chamber, the mass flow rate of the air is given. So ma dot is given as 100 kg per second. The stagnation temperature at the inlet and exit of the combustion chamber are given. So TO, TOI denotes the stagnation temperature at the combustion entry. So this is given as 600 Kelvin. And the stagnation temperature at the combustor exit is TOE, which is given as 1200 Kelvin, and the burner efficiency, combustor efficiency is 0.9, right? And the heating value of the fuel is given 40 megajoule per kg. Specific heats are given for both the cold gas as well as the hot gas, and we are asked to find out the fuel flow rate. So to find out fuel flow rate, we have to uh, do energy balance across the combustion chamber. Okay, so the total energy at the inlet and exit of the combustion chamber will remain same. So if we do that, so the total energy at the inlet of the combustion chamber is in a dot into COI plus it addition by fuel addition is mf dot into 40 10 to the power 6 into eta b, and this is the total energy available at the exit of the combustor. Mf dot Cp hot into, now if we just substitute all these values, so it will be 100 multiplied by 1000 multiplied by 600 plus mf dot into 40 into 10 to the power 6 into 0.9. So this will be equal to 100 plus mf dot into 1200 multiplied by 12. If we solve this equation, mf dot we will get as 2.46, I think. Okay, so this is the correct answer. Okay, so these are the solution of the questions from gas dynamics and propulsion part. Thank you.